Okay, well, we'll go ahead and get started. Let me go ahead and open us up in prayer, and then I'll give you a sense of what we're going to be doing today. I also talked about it during our last session. So let's just invite the Lord in our presence. So, dear Heavenly Father, Lord, thank you very much for the chance to be working with each of the students in this course, Lord. Pray that as we're finishing up, Lord, that this has been a beneficial experience for each student as they're getting a better sense of what it means to be an engineer, some of the ways that an engineer thinks, and how we can be glorifying God with what we're doing with these skills that we have been able to absorb. Also help in their spiritual formation, Lord, that all of the various incredible messages that we can be getting from Scripture, that they can take them to heart, Lord, and that they can be developing the skills to be using theological methods to see how to apply Scripture in various day-to-day experiences. And finally, Lord, give us all interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, today it's going to be a focus on all of you. And so what I wanted to do is give everybody a chance to go ahead and showcase their project work. And so what I'm going to do is stop sharing my screen and open it up for all of you to get a chance to walk through your information that you've gathered as a result of the doing system engineering. The last couple lectures, I was trying to highlight stuff that say folks from NASA, how they have done model-based system engineering and how that's actually been beneficial. And I've given you guys some outlines on how to be creating a final report and final presentation. So I'll just turn it over to you all. And who would like to go first? Maybe I'll just more or less randomly pick folks and say, Jonathan, would you like to go first and share about your project?
Sure. Do you want me to share my presentation or just talk about it?
Yes. Yeah, that'd be
Okay.
great.
Let me pull it up. Okay. Okay. Can you see it?
Yeah, great. It's in full screen mode. That's looks good.
Perfect. Okay, so for my project, I decided to model out the systems of a nuclear power plant. And to start off, the project mission was to design a functional and efficient nuclear power plant that can run safely and flexibly. So, a basic summary. When I first started this project, I had to research a lot into how nuclear power plants work. I at first had a very general idea, but this project kind of helped me to get a more in-depth view on how that works as a whole. And so that led me into three goals that I wanted to do. And so the first was flexible power generation. So with this goal, I wanted to be sure that the nuclear power plant could adjust its output depending on the needs of the consumers. So it could generate more power if needed or less power if people aren't consuming that much. And then number two was consistent power generation. Nuclear power plants run 24/7, so they're always producing power. So I had to make sure the system could run consistently without breaks. And then finally, safe waste management. The only downside to nuclear power is the nuclear waste. And so you need to have a process in which to deal with the waste that comes with that. So moving on to the project diagrams. My first ones I'm going to go through are the use case. So I have three use case diagrams. The first one was to highlight the initial turn on of the system. So that would involve activating the cooling system and raising the control rods to initiate the reaction. The second one was in the event of detecting an anomaly. So it would lower the control rods and monitor the temperature to make sure it stays stable. And if it doesn't, it would just drop them completely to stop it. Then the third use case diagram was to highlight the day-to-day operation of the plant. So it's constantly monitoring power consumption, power output, and adjusting the reactor as needed. And then the stakeholder in this situation would be the consumer. My NETS diagram was the requirements diagram. So these are all the requirements I want to go through in the system. So I highlighted 24/7 operation, refueling, maintenance, cooling, temperature management, flexible power, waste management, and storage, and protocols in case of any sort of disaster. And then my block definition diagrams. With these, I split it into 3 systems: the temperature management system, the power generation system, and then the power management system. And then in my NETS block definition diagram, I split these up into even more. So temperature management involves all the cooling stuff, such as the cooling tower, water pump, and the temperature sensor. And that relates to the power generation with the reactor and the steam generator and the output sensor. And for the power management system, it would just involve monitoring the power consumption and then the operator. And then this is my package diagram. So I split all this up. So the blue is the nuclear power plant as a whole. Then I split it up into the cooling system, the reactor, the power generation, the control operator, and the waste storage. And then these are split down even further. For the cooling system, you would need a condenser, so the steam would be able to be converted back into water so you can reuse it. A cooling tower, which allows you to do that without pumping the excess water and hot water into a river. And then a water pump to keep the water moving through the system. So, and then for the reactor, you need nuclear fuel, you need control rods to keep the reaction in check, heat dispersal, temperature system, and then likewise the other things that involve steam transportation, the control operator as a whole, so the terminals and the ability to change it, and as well as waste storage, which is just dry casks. So for my activity diagram, I highlighted 2 different processes. One would be regulating temperature. So if you go through here, it goes through the process in which temperature is regulated. And then over here, it goes through the process in which reactors are adjusted. For my sequence diagram, I just highlighted data communication throughout the system. So it shows the communication of data between the operator, the sensors, and how those all relate together. Okay, so for my state machine diagram, I have 2. The first one shows the initial turn on, so it involved testing the sensors, making sure those work properly because those are required for safe operation. If they don't, they would call for maintenance. If they do, everything else will be activated and turned on. Then for the state machine diagram, the other one, it highlights anomaly detection. So if there's anything unstable happening, it'll be able to detect that and stop it before it gets to unsafe levels. So for my internal block diagram, it just highlights the reactor, the things within the reactor, as well as some things of how it relates to some other aspects outside. So like the steam generator, the temperature sensor, and how it relates to the insides of the reactor mechanism. So for my parametric diagram, I decided to highlight 2 different constraints of the system. The first would be mass, and the second would be temperature. So the mass of the reactor vessel, the water pipes, and the nuclear reactor, I did a rough estimate. It would be about 241,000 kilograms. And then for temperature, the max temperature of the reactor should be 700 degrees Celsius. So going into required resources, just so these are rough estimates. You would need engineers, construction staff, city planning, and for a rough estimate of labor, construction, materials, and then for a basic schedule, 3 years for design, 1 year for testing, and 7 years for building. So through this process, I was able to learn a lot about systems design and systems thinking. As I stated before, when I first started this project, I only had a general sense of what a nuclear power plant was and how it functioned, and this allowed me to really map it out and get a deeper understanding of the system. And then on top of that, I was able to get a much bigger understanding of design. For example, I didn't realize how complex systems can be when you really break them down into their components. So that was what I was able to learn with that. Thank you.
Well, thank you very much, Jonathan. And that was exactly what I was hoping that people would be getting out of what you're doing with our project efforts in this course. And so, interesting enough, who would have thought at the beginning you're doing all these different diagrams that you're probably being exposed to for the first time, and literally by stitching all those together, you're able to create a narrative that was comprehensive to give you a sense of what's going on for a power plant. And so that's what a system engineer does. And so, so he may not be an expert on all of the details, but getting things together and stitch it all together in a coherent way is a useful thing. You also included programmatics that was nice just to get a sense of what would be the cost, the schedule, the resources, the external resources that you'd have to do coordination with. All of that look good. Probably about the only thing I could mention is like for the requirements, they should have the word shall, and I noticed that you had will in there, but that's we're all in a learning mode in this course, but that would be the one thing that I would mention. And so we could have easily spent a couple hours going in more detail on those diagrams, but this was what I was hoping for, is to get a nice summary discussion. Each one of you is doing a different project, and so now you're becoming a subject matter expert from a system engineering perspective, and you're trying to share that with others that that's not their area that they have focused on. And so hopefully this is one of the ways it's going to be encouraging for all of you to now get a chance to see a variety of experiences from different people of what they've done using this general approach, system thinking, and applying it to what you're doing. So thank you very much, Jonathan. Abby, why don't we have you go next?
Okay, I just shared the screen, right? For the
Sure.
slides.
It's a green button. If you just push that, you should be able to share your screen.
Can you see that?
It's getting there.
Let me see if I can get it full screen.
I
That's not it. Hold up.
love the title too.
Is it full screen now for you
Yeah.
guys?
Well,
Almost.
not almost. I'm not familiar with
How do
Google
you
Docs. It looks like that one that you,
how did you
how
make
about
it full
you could click on view? I think that's, you may be able to find, yeah, full screen is at the bottom.
Oh yes. Wait, what?
Hmm.
This one? Oh, okay, I got it. Okay, now it's good.
All right, cool. Good
Okay,
job.
yeah, so my project was called Gecko, which stands for Give Elon Competition Operation, because the goal is to design a new model of an autonomous vehicle to further the auto industry that's also a hybrid. So, of course, it would give some competition to the Tesla company. And then the summary of like what the plan would be is to make a new model of the autonomous hybrid vehicle again, and then it would use existing technology, but the design would be from scratch. And it would go to production of one prototype, and we would hire an engineering company to make most of the parts because we're only making a prototype. So it's not worth buying machinery that we would only use for one prototype. But we would have all the files ready. So if we patent it and sell it, then we would send the files to whatever company bought the design. The goals would be to design a new fully autonomous vehicle model, manufacture one prototype, provide safe transportation, and of course, give Elon Musk competition. And here's my first use case diagram. I have a description, but I'll leave the diagram up so you can see it. So basically it starts with the computer science department and the engineering department, and they would be simultaneously programming the auto drive, and then the engineering department would be designing the actual vehicle. So all the mechanical components, electrical components, the interior, And then a mechanic or a technician would interface all these components and then test it. And then the stakeholder would be the customer or the car company that's interested in buying the design. And then I made a second use case diagram to show the auto drive feature. Basically, the driver or the operator would select auto drive and input the destination, and then auto drive would operate the vehicle by monitoring surroundings, using GPS, and then steering. And then for the manual option, it would just be the driver doing all of these things. And then I also included that the passenger can do some of them too, like assisting with temperature, music, GPS, and assessing the road. And then here's my requirements diagram. It's easier to see when I just wrote it out, so it's not that tiny. So for production, it shall create an autonomous hybrid prototype within 10 years. For comfort, it should comfortably fit 5 people. It should be capable of reaching 100 miles per hour and meet all federal vehicle standards, be under 4,000 pounds total with a 2,000 pound battery pack. And then the battery pack would be 100 kilowatt hour battery pack, and then 100 miles per gallon equivalency for the efficiency of like using an electric battery versus a gasoline engine. For autonomous driving, it needs to be able to detect and obey traffic signals. It should have a response time under 2 seconds, and then the sensors need to reliably detect objects all around the vehicle. And then I have my block definition diagrams. So I think, yes, the first one I did high level. So it's just the vehicle with the frame, battery, auto drive, motor, and the tires. And it shows would these be stakeholders? The people involved. And then I did subsystem that went more into the auto drive. So the main parts of that were the computer, actuators, communication, sensors, and then a user override option to get out of auto drive. And yeah, and then all of those are broken into further parts. Then I have my package diagram. The main like categories were just auto drive, manual, and power. And then auto drive had computer and sensors. Manual had actuators, transmitter, receiver, frame, and tires. And then power has battery, like the electric battery, and then the motor, which is more like the traditional gasoline engine that it would need it for. And then those are broken into further groups as well. For the activity diagram, I did starting the car. Actually, I'll leave it at the diagram to see. So it would start with when the car turns on, it will start with the computer determining the speed. So it'll start less than 50 miles per hour because you're not moving at first. And it will go to the lithium ion battery, which is what electric cars use. And then that will send the signal to the controllers to send voltage to the motors, which will then turn the wheels of the car. And then if the speed gets over 50 miles per hour, for example, on the freeway, it would go to the lead acid battery, which is just like a normal car battery for a non-electric car. And then that would send a signal to it would align the cylinders with the starting motor, and then that will turn the wheels. For the sequence diagrams, I had one for auto drive, which is just the driver inputs destination on the display, which then decides the route with the computer, checks sensors with the cameras, and then that sends the signal back about the surroundings to analyze, and then display the location to the driver and display directions with the GPS. And then for the speedometer, it would determine the speed, the computer will choose the battery, like choose whether to go in electric mode or just like the traditional gasoline engine based on the speed. The batteries will start the motors or engine, which will turn the wheels, and that will turn the magnet and speed cup and dial in the speedometer, it'll just be a cycle that keeps sending the speed so it can choose which battery it should use. And then for the state machine diagram, here we go. Yes, so by default, when you like turn the car on, it will be using electric because the speed would be 0, and it'll be in manual mode. And then you can switch to auto drive by inputting the destination on the touchscreen. And then once the destination is reached, it will go back to manual. And then I think I already mentioned if the speed goes over 50 miles per hour, like if you're on the freeway, it'll start the gasoline, or yes, then it'll switch to the gasoline engine instead of using the electric battery. For the internal block diagram, I did it for the engine to show how you, just like the normal engine. So if the speed is greater than 50 miles per hour, it would, you would need fuel for the engine, which would turn the crankshaft, which will align the pistons, power the drive shaft, and turn the wheels. And then I also showed how the lithium-ion battery would connect to the wheels as well through the controllers and motor. And then this would be like a parallel hybrid car. And then here's the parametric diagram, so showing just the requirements for weight, how they all need to add up to under 4,000 pounds total. With the 2,000 pound battery, that's like the biggest one. That's like the biggest concern for electric vehicles. And then the frame would also be a very big chunk of that. And then if the vehicle weighs 4,000 pounds, it must be able to safely support 12,000 pounds, including its weight, in order to account for passengers and anything they need to transport, and then have a safety factor as well. And then the voltage would be a combination of the lithium-ion battery and the lead-acid battery because it's a hybrid car. And the RPM, or like the rotation speed, will depend on the crankshaft and the fuel tank. So overall, the required resources, I looked at cost, schedule, and staff. I estimated the funds would be about 62 million to get to one prototype. And this was like the calculation for the total cost. The schedule would aim to complete the prototype within 10 years. And the first 7 years would focus on designing the model. And then the actual like production and testing would be the last 3 years of that. And then I estimated 25 engineers and 15 computer scientists to program the auto drive, and then an extra manager to oversee each of these departments. And I accounted for that here too for the cost analysis. So overall, I definitely learned a lot about the tasks that systems engineers do, because I'd never used SysML or like a similar modeling software before this. And it made me focus on the bigger picture, because if you try to go into the smaller details of how each component works, your diagram would be way too large to understand. So I saw how system engineers have to think and like the process to complete the design. And then also I appreciate Charlie, which is the name I gave my car, a lot more, because now I see how much it takes to design a simple prototype or model of a car. So yeah.
Well, Abby, congratulations. Just like Jonathan, you took something that maybe you were interested in, and now you got a chance to flesh it out. And that's what I think is the magic of system engineering, is literally without having to doing a whole lot of heavy lifting. Remember my perspective that for a systems engineer, instead of having to work harder, he has to think harder. And so just to conceptualize how this would come together and how it would work is what you've done. Programmatically, I thought you did a good job of making a basis of estimates. You could think Elon Musk. It sounds like some of the tweets I've been seeing that he's been putting out lately, he seems like he's dealing with a lot of production. And so maybe there's something that he's calling the Model 2 that he's looking to put out. And so all of the manufacturing challenges are extensive. And so you gave an estimate of something like on the order of 62 million to get a prototype. And so that's like the non-recurring cost. And then there's a recurring cost, what it takes to produce every vehicle. I like that you were looking at a hybrid. Those are some of the things that are being debated. And so do you have just a strictly electric? That's what Elon Musk is doing. The Chevy Volt is an example where it is technically a hybrid. It has a gas engine that you could have as a backup. So there is a tendency of with electric car that you can get this anxiety. Is there going to be a charging station at your destination if you're not just going to work and coming home? So I think there's a lot of things that you have captured here, and you did a nice job of showing all of those things that you've been able to do over the semester. So kudos and congratulations. And I guess Elon Musk is going to get some good competition. So thank you.
Thank you.
Nathaniel, why don't we let you go next, and then we'll have Kyle give us his thoughts on his project for to close up.
Okay, yeah, cool. I can go next.
Good.
Let me just pull it up. Okay, yeah. You can hear me, right?
Yeah, we can hear you just fine, Nathaniel.
Okay, perfect. Yeah, so my project I called the Iron Studs. Why? Because I thought it was pretty funny. Because my project is supposed to be a system of missiles, basically, and I have the intent of designing for the United States Air Force. Why? Because I'm basing it off of Project Sentinel, which is a project that Northrop Grumman currently has, and I'll be working on later during the summer. Basically, what they're doing is they're trying to revamp the Minuteman III missile silos because they're well past their life expectancy. So it's about time to upgrade, you know. So that's what the goal of the project is. I was just curious, like, if you start from the ground up, about how long it will take and all that. But the actual project is just revamping kind of what's already there. So that's a lot better than, you know, building everything from the start. And the goal, so like pretty much overall in Project Sentinel, there's going to be 450 launch facilities and then 50 alert facilities. And, you know, each thing needs to have like supporting infrastructure for people as well as the missile. So that's pretty much what we're doing. We all know the types of diagrams that we have, so I'm not going to go over all of that. But I kind of, so like in each diagram, I have like a description after, but I'll just stay on that diagram.
Mhm.
So this one is just supposed to show like the typical operation inside a launch facility. So in a launch facility, I only picture like security being there and a maintenance squadron. The maintenance squadron, it shouldn't require a whole lot of maintenance, but just in case there's any unexpected problem, it can be dealt with right away. So on top of that, I mean, anyone who's there needs security clearance, but pretty much the engineers that would be there would be from the Army Corps or anyone else that has some sort of security clearance that the U.S. Air Force is okay with. And they just need to keep it operational and protected. So to keep it operational, they'll have like a control panel that shows them pretty much everything they want to know. And then they should have a good amount of infrastructure to see that everything is going smoothly and nothing suspicious. So that's pretty much most of the time what it'll be doing, because we don't want to have to launch every time, because these silos only have one missile. It's not like they have like a whole armada of missiles in there. So that's that diagram. This next one is supposed to show like the launch mode. So basically I only picture really having like a two-step authentication, and each code does something different. So one will be from the United States Air Force, which will just basically activate the missile and begin the actuation part. But the second code will come from someone who's on the particular site, probably like the head engineer. And I think that's a good way of doing it, because you want to make sure everything's safe and functional, and then you can open up the blast door. So like I picture that's the two things that are going to happen. That's pretty much all I'm showing in that diagram. And then this next one is just like, heaven forbid that there's, you know, a fault case, but if there is, we should be prepared for it. So I mean, we don't want those facilities to be taken over, but they should be in the US, so I don't really picture any land invasion, but I guess they should be prepared just in case. You never know. So, it's just they need to have some way of communicating if they're in, any distress sort of state. So that would definitely take priority. Lockdown, and the safe room is pretty much the control room where everything would be. So that's all I'm showing in this diagram. And then requirements is kind of just, I mean, it's pretty similar. So I'm just saying that you do have attack, which is the launch facilities I was talking about, but you also do have a good amount of defense and like communication patch through, because I picture the alert facilities having some sort of defense mechanism, not just like warning. But I mean, they will, their primary function will be warning and relay messages and trying to get intel. But they should have some defense aspect as well. And then just each building needs certain infrastructure that, I mean, we're all familiar with, like water, gas, electricity, all that. Like there's a good amount to be said for all of that, especially with like how much these facilities will be doing every day. So that's what I was trying to show in this diagram. Yeah, and then this was a higher level one. It's just, again, I just focused on the alert facility, or sorry, the launch facility. Like the main components are just the blast door is actually pretty good, because if there's ever a fault, I mean, you pretty much have one of two options. You can just detonate the missile, or you can disarm it, or whatever. So that's something that would have to be made and taken care of. But the blast door should be capable of containing that explosion. So that's a pretty crucial thing. You actually need that silo part, like the chamber, and then the missiles obviously stored in there because you only have the one. And then the control room, which will pretty much have everything, and you need somewhere for the guards and everyone to sleep. So that's what's in there. But at a higher level for the missile, there's several components really, but pretty much the main thing is that like there's different phases for the missile to go through. So I think that's kind of worth noting, because you have like 3, maybe 4 propulsion stages, and that really like determines how you want the missile to break apart. So like I would say at minimal 3, like 1 is to break the atmosphere, 2 is to travel where you want to go, and then 3 is coming back down with all you got. 4 would just be like maybe a final kick in the right direction. So there's a lot happening there when you break apart. And each thing needs to kind of be adjusted for a feel and so forth. And so because you want it to also break apart, it'll change a lot of what's going on. But I mean, that's the main thing though, is that you want it to break apart and you want it to be going as fast as possible and efficient as possible. And then I would say you also want some communication on there, because yes, you should do a good amount of calculations beforehand to get the exact trajectory you want. But in case there's any like unexpected circumstances, I think there should be a way to kind of adjust the missile. So I would say that communication line is very important. And then like to know if anything is going unexpected, you need to know values. So you need some sort of sensors, and if you're going to make adjustments, you need some sort of way to actuate it. So that's what I was trying to show there. And then of course, for all that stuff, you need power. It's not like it just comes from nowhere. So that's what I was showing in that diagram. And then the package diagram, I just did both the launch and alert facility, but I think it's pretty straightforward here. I mean, we can focus a little bit more on the alert facility. I think there should be a good amount of communication capabilities there. I think you need a lot of different antennas and tracking, like infrastructure, just so that you can see, because I'm sure you want to know what's in the sky. You just don't want to, like, you don't want to rely on something else, especially the Air Force. I think they should definitely have ways to track pretty much anything and send all sorts of signals up there so that they know what's exactly overhead. So that's kind of what I wanted to show in that one. And the other stuff we already pretty much talked about from the other diagrams. And then the activity diagram, I was just showing like what would happen when you go to enter the codes. I think the main thing here is just if any code is wrong, it's pretty much going to lock down the facility and send out an alert just right away. Just you don't have multiple chances that code is right or wrong. And if it's wrong, it like that definitely needs to be noted to just about everyone, especially the president should be alerted. Well, and the Air Force, if and when it's activated or if something was wrong. So that's pretty much what I was trying to capture there. But that the alert would happen only if it's wrong, and then actually when it fully has launched. And then after launch, we're gonna like the other thing up here I was trying to show is just that you stay like. I picture the missile kind of having like what I would call like an umbilical cord, like everything that it needs is coming from there just to make sure it's all charged, it has everything it needs. There's a communication line already established. You know, I mean, so that would need to detach before, but I would just wanted to show that. Yeah, and then the sequence diagram, I was just talking about kind of like the adjustment part. So I kind of mentioned it, but the first thing is that you need to kind of know where you're at and how you're oriented. So not just like where you're moving, but how you're facing in that way. And like if you're jittering too much, I don't know how else to describe that, but like jittering, like you're kind of like you're shaking. So you need to know like translational, rotational, and if you're, I think it's called jerk really, but so you should have sensors for all of that, and you should know well beforehand of what the weather conditions are like when you launch, because that'll change it a lot. But there really should be calculations done beforehand, so it's not like the system will know everything. Like there still needs to be calculations before you launch. But like I was saying earlier, in case there's any need, you should have that option for like some sort of override. So the CPU should be checking for that. And you do need communication to do that. So that communication line is very important. So you should have a planned trajectory and a planned communication thing, like a network. And then you should just be constantly checking for it. So that's what I was mainly showing in there. And then yeah, this one was more just about opening up again. So I kind of already mentioned the stuff with the door opening. Like you do need to know that that's actually moved before you put that up, because that would kind of suck if the door didn't open and then this just jammed into it. So you should have could you imagine? So I mean, you really should have that confirmed. And I wanted to show like, I think for pretty much everything, like when I say a control panel, I mean like flags will be sent by other sensors. So like, yes, when the door opens, like almost like an LED should come on, right? Like something simple like that, where it's like, yes, this is working. This is doing what it's supposed to, or at least my sensors say it's doing what it's supposed to. And then so this is the other thing too. I don't just picture the missile staying at the bottom. I picture it raising up, because I want the attachments to come off pretty smoothly. So if I just raise it up slowly, it should be fine and it should come off pretty quickly. Because I do want it attached. That way I can check if it has everything it needs from what our calculations say before we launch. And then once all that is confirmed, then I can, cut the umbilical cord basically, and then it can go and launch and do its thing, and hopefully meet its target. And yeah, that's pretty much all I wanted to say there. And then for my internal block diagram, I just did a transceiver, which is like communication stuff. So I mean, basically you have your receiver, your transmitter, but I mean those, and your antenna. Like that's pretty much what it is. But like circuitry wise, it's not there's kind of a lot of detail that goes into that. So we could kind of go through it, but it's basically like when the antenna comes in, if you're receiving, it's going to be an analog signal, and the overall thing is to convert that analog signal into a digital signal so that we can feed it to our processor. And so there's kind of a lot of circuitry that has to pass through. It's not like you can just go from an analog to a digital converter and that's it. You need to pass it through some sort of filtering. So I have like a band pass filter going to like a low noise amplifier and then a mixer, and then it actually gets converted to digital, and then we're stepping it down, then we're filtering it again, and now it's at the CPU. So that's like the receiver side, and then the transmitter side is okay. So so we're wanting to send a signal from our CPU, right? So it's going to go through its filter, a lot of filtering in all these stages. So you can't just it doesn't just magically work. You have to do a lot of filtering all the time. So that's what I was trying to show, because I mean, it's not something you really think about, all that filtering that has to be done. I mean, the unique part is kind of at the end. It's kind of like in reverse basically, but at the end when you're transmitting, you want to put it through like a high power amplifier, and then you can send it out on the air. So that's what I wanted to show there. And then the last thing with the parametric diagram was just, I think the hardest part overall is reliably getting that missile up. Like stage 1 should be the hardest part of the flight. So just trying to make sure that you balance how much thrust you can actually output and how much you weigh. So, I mean, from what I saw, it looked like you had to have about 3 times a thrust capability of your actual weight. And so that's kind of a difficult thing to manage, because you also need enough fuel. So you're fighting weight of the fuel versus like your capability to output. So, but as long as you're 3 times, you should be pretty much okay. So that's what I was showing there. And then you just need adequate voltage for all your systems, however much you want or how little you want. And I would say you should have at least for double of whatever it would consume on your flight. So, but I mean, that's easy enough to over design, over engineer. Yeah, and then required resources. So actually, this number is pretty low for, I mean, like I know it seems high, but for how many workers would be on this, it is not a cheap project. So I have it for 25 years, and I think at pretty reasonable salaries for people.
Yeah, this is like a life cycle cost. And so
Yeah,
you'd have to, if this is for a government program, so they'd have to be, that if it's over 25 years or 20 years, then you amortize that over that 20 years, and then it starts to be a little bit more, quote, reasonable. But yeah,
Mhm.
you're getting a chance to be thinking about those things. That's good.
Yeah, so I tried to show that in that diagram, and this, I mean, this one, I think like this stuff would actually cost a lot more than what I put on here, because even though this, I mean, it sounds fairly reasonable, all those numbers, but in actuality, when I was looking at it, that's what I was getting to right here. From last I checked, okay, they actually have an initial investment of like 13 billion. I was asking for 8 billion. Now their project, they're saying, is around 130 billion. So that's quite a big difference. That's a lot of money. And where I was saying it would only be 25 years, when I went for the interview, they had said they had planned on finishing like 2085. So it's not a quick project. It's like
Yeah.
so it's like a career project.
Yeah, it's a long-term capability.
Yeah, and that number had grown because they had originally started off with 96 billion is what they were asking for, and now it's up to 130. So, but there's improvements being made, so I think it's worth it. But cost wise, it's kind of alarming how much it requires. So I thought that was worth noting. And then results, like just overall, like Abby, I think I kind of had a misconception of what system modeling was. I was picturing like CAD or CAM or like the computer aided engineering with simulations and stuff like deformation, like stress analysis, that type of thing. So I kind of had that misconception. And the other thing was I didn't realize I was kind of thinking systems engineering was more like bottom up. So but the top down makes more sense, especially for like a large scale project. That way you're covering everything. I think I was just thinking bottom up for like a just because all the projects I've done have been pretty simple or they're not super complex. Um, so that was definitely a different viewpoint that I didn't even think about. So it was kind of nice to see it from that perspective. And then, I feel pretty good. I feel ready to ask questions and learn more for the summer. So, yeah, that's it.
Well, congratulations, Nathaniel. And if you would like, feel free to share this with your intern company with Northrop Grumman and see what they think. You could say that, well, this was just basically what I could get just doing internet searching, doing some basis of estimation, thinking as a systems engineer. And I'd be curious to see what they would say. You were also mentioning like CAD development and all of that. Those are some things that come, I would say, next, but you sort of have to get a landscape to help you figure out where you're going to start to do that. And also within the construct of how much time we have in this course, we really didn't have the time to do all that. I also saw that some of your diagrams got very detailed, and that is definitely something that starts to happen as you develop more and more a model-based system. That those models can get more and more complex and they can have multiple layers. And so I think you were showing a lot of good detail in some of the things that you captured. So congratulations. I also, you can see that each one of you were very cogent and able to communicate about your project fairly well. And so the diagrams are part of what a system engineer does, but being able to do that system thinking and put together an understanding of what the mission is and how it's going to be accomplishing that mission. I think you guys have done a great job on that. So thanks again. Nathaniel, let's finish up with Kyle. Why don't you tell us a little bit about your project?
Thank you.
Sure thing, Nathaniel.
Okay, so see mine, I was a bit confused on like what exactly I was supposed to do for the slideshow. So I didn't like have all of my slides really just, I really just put up the ones that I felt were most presentable. So let's see, where is the thing? Okay, okay, you see that?
Okay, good.
So yeah, let's see. So this is my requirements diagram. Yeah, it was. So you can see it starts out with sending photos to ground, and so it needs like the power to send those photos to ground. And I also realized that a pretty integral part of the system, as I was planning this out, is that like it needs to be able to tell what side of the Earth it's on, because obviously it can only charge, it can only take pictures, at least useful pictures, when it's on the bright side of the Earth. So I'm pretty sure the best way to do that is just like be able to tell if you're getting charge from the solar panels on it. And then on the dark side, you can use that time to process the image. And but also you need to be able to override that dichotomy by like actually sending photos to the ground station. So you also need to make sure that you're not like running out of power, because you're only getting power on the bright side, and you're gonna need power to process the image and send them to the ground station. So that's kind of the whole dichotomy I had to deal with. Here's the state machine diagram that kind of helped figure that out. Yeah, obviously the ones going from active and processing to sending, those should be two-way arrows. Yeah. So yeah, I think this pretty much goes over all the states I mentioned. So it's just
Mhm.
if it's above ground station, then it sends its highest priority is charging. If it's on low battery, its next priority is to send. And then besides that, it's just the cycle of being active on the bright side of the earth and processing on the dark side of the earth. Let's see. And here's the block definition diagram. We have solar panel. And then we have the solar panel goes into the battery, and the battery powers the infrared cameras, normal cameras, and the Raspberry Pis. And let's see, use case diagram. I couldn't really tell what exactly to do differently from the state machine diagram for this one, so just pretty much the same thing. And yeah, that's it. I didn't really know what else to put in the slideshow.
Well, thank you very much, Kyle. You can feel free to reflect on what other folks have done with theirs if you want to augment it a little bit more. But even still, with what you had, like everybody else, you were able to tell a story. And so everything you did in SysML was one of the contributions to help you to make a cogent story about what you're trying to accomplish and to be thinking about it from a systems engineering point of view. So once again, I want to say thank you for everybody for what you shared. It was a pleasure to pass on the vision and see how you guys individually have took that to heart and developed something that you found interesting. And so hopefully this is a skill that you can be leveraging in your future. And so kudos again. So I think that's a good breaking point for us. And so I will meet you all next Tuesday, and we'll do a review of what we've talked about for the semester, and that will be an enjoyable way to be reflecting about all the material that we've had a chance to get exposed to. Okay, well, God bless you all. I hope you have a wonderful rest of your day, and we'll talk soon. Take care.
Thank you. Have a
Thank
nice day.
you.
you.
Yeah, thank you.